All right. Welcome to stage 6, everyone. Grab your headphones, put them on if you haven't already. My name's Aaron Peterson. I'm a solution architect here at AWS, and we have a great topic for you today. I can see the people streaming in. This is awesome. A few housekeeping things to begin with. If for some reason you don't have your mobile phone on silent, please do so. You probably won't notice, but the speaker probably will, as they don't have headphones on. If you are having a problem or you see someone around you is having a problem with their headphones, just raise your hand and we'll endeavour to get round to you and do a bit of a swap. Feedback is really important, and we have the app where you can give feedback. So at the end of the session, you'll be able to click into this topic, and then it'll have a little button to say complete the survey, and we would love you to do that. This session is going to be an absolute great one. This is Sayem coming to talk to you today about a really complex data problem and how to solve that. So without further ado, I'd love to bring to the stage Sayem.
Thank you. Hello, everyone. Thank you for joining our session today from Stream to Lake, Architecting Real-Time Transactional Data Lake. My name is Sayem. I'm a streaming data architect at AWS. I've been working with AWS for over 10 years, helping customers globally, designing and building data platform at scale. So in this session today, I will talk about how you can build a modern data lake leveraging transactional capability on Amazon S3. I will deep dive on AWS native capability for streaming ingestion into your transactional data lake. I will also share some of my perspective working with hundreds of customers, especially some of the common implementation challenges, and how you can overcome those challenges with AWS native capability. Let's talk about the reality first. I think all of you will agree with me that the traditional way of building client-server-based architecture, where your application is just pointing to a database, is no longer true. Of course, these databases are still one of the primary source of operational data the way we do CRUD operation, which means create, read, update, and delete operation. But we also see a diverse ecosystem of devices, application, microservices, generating data that are no longer relying on database as the first entry point to store those data. And in this situation, we also see the way we want to consume data is different. When a fraud is detected, you want to get that information immediately. When you're doing financial transaction, for example, deposit or withdraw, you want transactional capability from the system for data accuracy and consistency. And you also have an analytical need on the same data for reporting purpose to understand deeper on what's happening within your business so you can take a data-driven decision. And since you have more data, you want to build a smart machine. And this smart machine can take better decision, can predict the next course of action on your behalf. And this smart machine, what we call in other words, is machine learning model. So, and the situation of diversified data sources leads to the requirement to have unification of the data into our data lake. Because as in business, we want to get a complete view of what's happening. For example, knowing about customer activity and the customer preference all together. And we also want to get the event visibility as soon as it occurred. And we want to feed the relevant information to our end customer or end user. As I said earlier, database is still one of the major sources of operational data, the way applications interact with the database. So let's talk about 2 examples where you need your operational data into the data lake. And the common term we use to get those data from database in real time, we call it CDC or change data capture. And 2 popular database right now is Postgres and MySQL. For example, a fintech company want to sync their Postgres transactional data into their data lake so that they can use different analytical and machine learning tool to access the same data. Another example could be retail company want to replicate their MySQL data into their data lake, and they choose data lake over data warehouse because it can reduce their storage cost, and they can use the same multiple analytical and machine learning tool to access the same data. And for streaming data, usually we use a streaming engine for buffering, real-time notification, real-time dashboard update, and so on. But there is a growing demand to move those data into the data lake for other purposes. For example, a gaming company want to move or replicate all the data generated by their gaming platform into their analytical system. And they want to handle large data set into their analytical system, and they need partition evolution capability into their data lake. Another example could be a connectivity intelligent company need to analyze network metrics data streamed from their client devices to Amazon S3. And they need row-level deletion capability into their data lake for GDPR compliance. So with all these use cases, you will see some of the common technical requirements. The first one is when you're moving data from your operational store to your transactional data lake, you need a consistent view of the data. You also need a scalable platform so that you can store data as much you want. And for this unified data, you don't want to just store it with the engine-specific format. You want to use many different data processing tools which can be accessible by this data that you are storing in your data lake. And then you want easy integration with your operational store to your data lake so that you can easily move data from your operational store to your data lake. There are two distinct challenges you will see here. One is the data movement challenge, which I will discuss later a bit more. And another one is the challenge with storing data into your data lake. Well, now why is that? Now, the data lake is fundamentally different than database. Think about it. In a database, you are continuously doing insert, update, and delete operation. Now, when you're moving those data to your data lake, you will face challenges on data consistency and data quality, because these managing those operations is much more complex into your data lake. And the second thing what you will observe is when you're storing more and more data, you will notice two things. One is the slow query performance, and you need to continuously perform complex table management strategy to get the performance that you need. So to overcome these data lake challenges, you can use Apache Iceberg. Apache Iceberg is an open table format that brings database level capability into your data lake, and it can handle large scale analytical workload. So let me walk you through how Iceberg solve our data lake challenges. First, as I mentioned earlier, it can handle massive amount of data. You have terabytes of data, billions of rows in a table. Iceberg can handle it smoothly and easily. And it supports flexible table modification that can handle all the concern I mentioned earlier. For example, if you have a schema changes, you want to do some changes on your column attribute, Iceberg can handle it smoothly and easily. And with dynamic partition management, it addresses the problem I mentioned earlier, where you don't need to do manual partition optimization. And here's something interesting about Iceberg capability. It provides engine flexibility. No matter whether using Spark, Flink, Presto, or other data processing engine, Iceberg works seamlessly with all of those engines. And with time travel capability, you'll be able to query data as it looked at a point in time. And with ACID transaction support, you will get a level reliability right into your data lake. Iceberg has two layers. One is a metadata layer and a data layer. And this metadata layer gives all the benefit of transactional data like I mentioned earlier. For example, like time travel or schema evolution and so on. And the data layer is where your actual data is stored. It could be in a Parquet format or in a WARC format, for example. So the Iceberg combination of data layer and the metadata layer gives all the benefit of transactional data lake I talked about earlier. So if you see in the screenshot, this screenshot is a S3 bucket, which is actually a Iceberg table screenshot I created with a tool called Amazon Athena, where you see a metadata and the data. But Iceberg also need a meta store to track all the changes within your table, Iceberg table. And for such, you can use AWS Glue. AWS Glue has integration with Apache Iceberg as a meta store. So awesome. We solve all the problem related to storing operational data into our transactional data lake with Apache Iceberg. So let's now focus on the second problem I mentioned, data movement challenge. So in the second problem, we still need to collect all the data from our operational store and then move it to our transactional data lake, right? For example, data coming from your MySQL or Postgres, or real-time data coming from Apache Kafka running on Amazon MSK or Kinesis data streams. For example, to read the CDC data from your relational databases, like MySQL or Postgres, one of the popular connector you can think of Debezium. This is open source connector you can use to read CDC data. But then again, you have to host this connector into a infrastructure. It could be a popular way you can think of hosting those connectors is Kafka Connect or in a container environment. And then again, to sync those data to your Iceberg table, you also need an Iceberg sync connector. Again, hosting it in an environment like Kafka Connector container, and then you can write it to your Iceberg table. So as you see, there are so many moving parts to move data from your operational store to your data lake. And while working with many customers, a few of the common challenges I observe, especially with self-managed connector, are first off, you need to manage that connector infrastructure by yourself, like provisioning, thinking about capacity planning, deploying the operating system, and so on. It's not just plug and play where you can bring the connector and it will run by itself. And you also need to continuously think about updating the connector, whether maybe it is because of a security patch coming, or there is a new version, or there is a bug fix. That's why you have to continuously update those connectors. And that can quickly turn into a maintenance burden for you. Another big one, right-sizing the connector infrastructure. I can tell you this is very hard to do. Most of the easy way to solve this problem is you provision for your peak load. I think you will understand my pain here as well. It's very hard to optimize that. And another interesting thing is you cannot scale down to 0 when there is no traffic on your environment. And there is another thing is high cost, especially during volume fluctuation. Because most of the cases, when you're building a streaming data pipeline, you will see that there is a unpredictable workload also coming. And most of the cases, you will apply policy based on the CPU. But the streaming data pipeline workload is IO-bounded workload, not CPU-bounded. So that does not work well with the policy that you have applied, so which means, again, higher cost. So all these add complexity and cost, and that's why many of our customers is actually looking for a fully managed alternative. And that brings my discussion to Amazon Data Firehose. In a simple way, you can think of it is a managed connector ecosystem to reliably deliver data into your destination. The service automatically provisions the infrastructure for you, and you don't need to scale up and down. It can do it automatically on your behalf. It provides powerful capability to transform data before it delivered to the destination. And Firehose supports 20+ sources and many different destinations, including Amazon Redshift, HTTP endpoint, Amazon S3, Snowflake, and many others. But for today's discussion, I will just focus on Amazon Data Firehose Iceberg capability. So with this capability in Firehose, you get a fully managed serverless solution that eliminates the need to manage any infrastructure. There is no requirement to deploy any server or bring any connector or thinking about patch deployment and so on. It can automatically scale based on the throughput on your environment. So with Firehose, you only pay for what you're using instead of over-provisioning the capacity to move data from your operational data store to your transactional data lake. And Firehose provides a no-code and easy-to-use solution for delivering real-time data into your Iceberg table. Now, with this approach, with the Amazon Data Firehose, you can now move your data easily. Using AWS API or AWS console, you can think of where you connect with your source database or a Kafka stream or a Kinesis data stream. And then you select your destination Iceberg table, and you create the stream let Firehose manage rest for you. So when you are replicating CDC data from your relational databases, as of now, Firehose support 2 relational engine in 3 deployment mode, which means it can be Postgres or MySQL, and it can be deployed in Amazon RDS, Amazon Aurora, or in a self-managed environment. And as an Iceberg destination, it can be a self-managed Iceberg in Amazon S3, or you can also use Amazon S3 table. For those who are not aware, Amazon S3 has added a new capability called Table Bucket, which is purpose-built for tabular data store, and it has built-in support for Apache Iceberg. Now, for real-time data, Iceberg has integration with many different sources, including third-party solution as well. For example, if you are running your Kafka workload in Amazon MSK, it can read from your Kafka topic, and then it can reliably deliver data to your Iceberg table. You can even use AWS API to directly put data to Firehose, and Firehose can reliably deliver that data to your Iceberg table. Now, I will go a bit deeper about some of the characteristics Firehose works with Iceberg. The first one is about routing data. So when you are capturing data from your operational store, you might have a different routing requirement to route data to different destination table. So it could be routing to one Iceberg table or routing to multiple Iceberg table. So if you have a logic where you want to route data to a single Iceberg table, the simplest way to specify those operations would be using JSON query expression. So as you see here, I'm specifying a JSON query expression with a database name user event, and where it will send data to customer ID table. You can also route data into multiple Iceberg table from one single stream. So let's consider a sample input here. For example, when I'm receiving a device ID with device ID 1234, I want to route that data to a table called device ID 1234. And similarly, when I'm receiving data with device ID 4567, I want to route the data to device ID 4567. Now, to route this record in a cost-effective way, you can specify JSON query expression. And in this example, I have 3 parameters, as you see, where I'm specifying the database name, table name, and the operation. By the way, the operation is optional. It could be insert, update, or delete operation. And if you don't specify any operation, the default operation would be inserting a new record into your Iceberg table. Now, for routing record into a table, you can specify a static value or a dynamic value. In our example, since we want to route record based on the device ID dynamically, that's why we are specifying a dynamic value start with dot. And that will indicate Firehose to look into the incoming payload and look into the exact column name and the value to route your data into multiple Iceberg table. But there could be more complex requirement you have where you cannot just use simple JSON query expression. You might have more complex rule. For example, you might want to, when your incoming data comes with A, B, and F, you want to route those records to a table called table T1. Or you might want to augment your incoming record by adding a new attribute or doing some additional transformation before you send it to your Iceberg table. So in such case, you can use AWS Lambda within Amazon Data Firehose to do those transformation, and then Firehose will use this instruction to route your record into multiple Iceberg table. So let's now focus on how Firehose handle insert, update, and delete operation. So you can apply insert, update, and delete operation into your Iceberg table with Firehose. The simplest and the most cost-effective way, as you have seen earlier, would be with JSON query expression. And when you source the database, Firehose read transactional log. And transactional log record all the database changes like insert, update, and delete in the order it committed into your database. So Firehose read all those changes, apply the same thing into your Iceberg table. Firehose support merge on read when it is writing to your Iceberg table. This is a table update strategy where when Firehose is dealing with update and delete operation, it writes a small file into your Iceberg table. So this is important, especially when you're dealing with streaming data and you want to get higher write performance into your Iceberg table. So what happens is, when the reader is reading, reader need to merge all those changes with the base file before it show you the latest view of the record. And when Firehose is writing to your Iceberg table, it write in Parquet format. This provides superior read performance from your Iceberg table. And Firehose support exactly once delivery of your CTC record in case of any failure and retry happening as well. Now I want to talk a bit more about how this update and delete operation works. Insert is simple, right? You just want to insert a new record. But for update and delete operation, Firehose needs some additional instruction from you. So it could be during your stream creation. So when you create the stream, Firehose stream, you can specify a unique key. And that is required to handle that update and delete operation into your Iceberg table. But if you don't configure that unique key, Firehose will look into identifier field ID into your Iceberg table. So when you create the Iceberg table, you can specify a identifier field ID. But what if both are missing? Like unique key is missing, you have not specified it, or identifier field ID is missing. So in that case, the operation will fail. It cannot write it to your Iceberg table. But providing that unique key during stream creation is optional. You don't need to provide it as long as you have a identifier field ID into your Iceberg table. For data delivery into Iceberg, you can configure a buffer time and the buffer size. Within that time, Firehose will hold those records into the memory before it flushes to your Iceberg table. For time, you can configure from 0 second to 900 second, and for size, you can configure from 1 megabyte to 128 megabyte. Of course, higher buffer hint means smaller write to S3, larger file, less compaction, faster query runtime, but with, of course, a higher latency. But if you have a lower buffer hint, it means it can write fast, but with a lower latency as well. You can even configure 0 second as a buffer time interval for real-time delivery into your Iceberg table. For CTC data, there are some interesting capability Firehose provide out of the box. For example, it can create the Iceberg table automatically by looking into the schema into your database. And it also supports schema evolution automatically. If you're adding a new column, Firehose can capture that and update your Iceberg table as well. And you don't need to expose your public endpoint to connect with your database. Firehose can connect within your VPC to connect with your database. Here's some additional capability I want to highlight. For initial copy of the snapshot, especially when you're reading CTC data, Firehose uses an incremental copy approach with watermark to track how far it has processed from your database. And this incremental copy approach helps to resume copy from where it is stopped and then recapture the table if any interruption happen. And Firehose uses a watermark table into your database. You can establish cross-account connectivity to connect with your Kafka workload running in Amazon MSK, and for that, it uses MSK multi-VPC connectivity feature. Firehose also integrated with Amazon CloudWatch for monitoring and logging, and it also exposed some of the specific metrics related to Iceberg as well. For example, the number of bytes it has processed from your source, and number of bytes it has sent to your Iceberg table, or how long it takes to run the JSON query expression, and so on. For encryption, Firehose supports server-side encryption with AWS managed key and customer managed key. And when you're connecting with the database, you don't need to specify user ID and user ID and password in plain text. Firehose can read that secret from Secret Manager to connect with your database. So that's all I want to share today about the Firehose capability, and then how you can write data into your operational data store using Amazon Data Firehose. But before you go, I want to share some additional resources that will help you to dive deeper and put today's concept into action. So in this slide, you will find 3 QR codes. The first one is the hands-on lab, which will help you to understand how to build a pipeline to connect with your data sources and then write it to your Iceberg table using Amazon Data Firehose. And second and the third one is the public documentation, and also the blog post will explain a bit more about the capability of Amazon Data Firehose integration with Apache Iceberg. Thank you all for being here today. I hope this session on building transactional data lake with operational data using Amazon Data Firehose and Apache Iceberg has been valuable for you. Feel free to connect with me in LinkedIn if you have any follow-up query. And if you could spare a moment, please share your feedback on your mobile app. Your feedback matters to us. Have a great rest of your day.
Thank you very much, Sayem. That was great. I will admit, I